Yep, we're good.
Good morning, everyone. Welcome to UNSW MathSoc and ELSOC Presents the Math2A Revision Seminar. I'm Jonathan, and I'll be one of your hosts for today alongside Oscar and Otto. So what will we be covering today? Today we'll be mainly focusing on vector calculus, and tomorrow we'll be focused more on complex analysis. So I will be presenting the curves and surfaces, differentiable functions, double and triple integral sections, while Oscar will be presenting vector fields and line integrals and surface integrals. So let's get started. So what is a curve? Well, I guess the definition of a curve is that the parameterization of a curve in Rn is a vector valued function equal to C, where I is mapped onto Rn and I is an interval on R. And a multiple point is a point through which the curve passes more than once, and a curve is closed if the value of Ca is equal to Cb, where A and B are the endpoints of this curve. Limits and calculus for a curve. So let's see our I mapped onto Rn be a curve with components Ci, where I is equal to 1, 2, or n. If the limit of t approaching a, Cit, exists for all I, then the limit of t, a, approaching a, Ct exists, and the limit of Ct as t approaches a is equal to the limit of C1, the limit when t approaches a of C1t, C2t, so on and so forth. So basically, if the derivative of Cit exists for all I, then the derivative of Ct is also equal to the derivative of C1t up until Cnt. And basically, the derivative can be interpreted as a tangent vector or the velocity at t. And the second derivative is equal to the acceleration. And here are 3 different ways to plot surfaces in R3. You can do it using a graph, implicitly, or parametrically using other vectors. So here's a past exam question. Suppose S is a surface given by x squared plus 3y squared minus z squared equals 1. Sketch the intersection of S with the x, z, and xy planes. Label your axes carefully and identify intercepts and asymptotes, if any. Identifying any known curves by name. So let's start with the intersection with the xz plane. The intersection of S with the xz plane will occur when y equals 0. So what we end up getting is xz plus 0 minus z squared equals 1. And we know that this is equal to a hyperbola, which looks something similar to this, where let's say we mark x as the horizontal axis and z as the vertical. We'll end up getting a graph that looks kind of like this. Where it intercepts the x-axis at the points 1, 0, and when x is negative 1. And then the intersection of S with the xy plane occurs when z equals 0. So in this case, we end up getting an equation of the form x squared plus 3y squared equals 1, which is actually equal to an ellipse. So if we were to Yep, so if we were to just plot it here, x, y, we'd have x-intercepts at 1 and -1, and then y-intercepts at 1 on root 3 and -1 on root 3. I apologize for my poor handwriting. Okay, some more things to note. A multiple point is a point on the parameterization of a curve that is passed in at least two distinct values of the time parameter. And a closed path, as mentioned earlier, is just where both endpoints are equal to the same point. So now let's move on to differentiable functions. Yes. So basically here we kind of have the formal definition of a limit, which basically just says that for every epsilon greater than 0, there exists a value of delta which is greater than 0, such that if the magnitude of any x value minus, or xy value minus ab in this case, is less than this delta, then the value of the function at the xy minus L should be less than epsilon. Basically, what this is saying is that as we kind of approach a specific point AB, then the function should approach L. And a function f, where I'm just going to say D is a subset of the mapping of R2 onto R of two variables, is called continuous at AB in D if the limit of x, y, when x approaches A and y approaches B, is equal to f A of A and B. And we say f is continuous on D if f is continuous at every point where A and B is in D. So consider the function over here. Prove that there is no value of L for which the function is continuous at the origin. So we know that the origin consists of the points where x equals 0 and y equals 0. So we just want to find a value of L that is suitable for f of 0, 0. And if not, then there's no value of L where it is continuous at the origin. So first we consider the limit when y equals 0. In this case, we just substitute y equals 0 into the equation above to get 3x squared on x squared, which is equal to 3. And then we consider the line x equals 0. So when we substitute x equals 0, we actually end up getting -5 y squared on 6y squared, which is -5 on 6. And that is clearly not equal to 3. So basically there is no value of L such that f xy is continuous at the origin. Okay, and now for partial derivatives. The first partial derivative f of x with respect to x of a function f of two variables is the function of two variables obtained by holding y constant and differentiating with respect to x. And you can see what this is defined as. And then similarly for fy, we just hold x to be constant and differentiate with respect to y. And as for the chain rule, suppose that f is a differentiable function of two variables x and y, and x and y are differentiable functions of two variables s and t. So then if a function in terms of s and t is equal to another function in terms of x and y, where x and y are also, I guess, functions of variables in terms of s and t, then the derivative of f with respect to s is equal to the expression just there, and likewise for the derivative of f to t with respect to t. This is kind of similar to just like, I guess, basic high school math. let's do another past exam question. If z is equal to a cubed plus 2b plus c squared, where a is equal to uv, b is equal to 2u plus 3v, and c is equal to 5v squared, use the chain rule to find dz, the derivative of dz with respect to du, when u is equal to 0 and v is equal to 1. And note that this is the partial derivative. Yep, so basically we just write out dz with respect to du in terms of all three of these a, b, and c variables. So dz on, yep, as it's given here, it's equal to the derivative of a cubed with respect to a times the derivative of a with respect to u plus 2 times the derivative of v with respect to v times the derivative of v with respect to u plus the derivative of c squared with respect to c times the derivative of c with respect to u. And if we just quickly compute it down here, this is equal to 3 a squared times v plus 2 times 1 times 2 plus 2c times 0, and which equals 3a squared v plus 4. And then if we substitute a squared, or if we substitute a equals uv into this equation, we get u squared times v squared times v plus 4, which is equal to 3u squared v cubed plus 4. And if we substitute u equals 0 and v equals 1 into this point, we end up getting a value of 4. Okay, and now for a Jacobian matrix. If all partial derivatives of f exist at a point A, then the Jacobian matrix of f at A is given by the matrix shown below. So basically, each row corresponds to, I guess, like the value of f you're computing, and each of the columns corresponds to a different variable you're differentiating with respect to. So for a total differential, if f with respect to x and y is a function whose partial derivatives exist, then the total differential of f is given by the sum of these. And the total differential approximation of the function f x y at the point x0, y0 is given by a slight manipulation of the total differential, where we also include the delta of the change in x and the change in y. Now for the gradient, suppose f is a function of two variables and fx, fy are continuous at the point AB, then the gradient of f is just equal to partial derivative with respect to x and partial derivative with respect to y as like a vector. Then for a function of two variables with a gradient that's not equal to 0, the maximum and minimum values of the derivative of fx0 are plus minus the absolute of the gradient of the function at the point, and occurs in the directions given by that sign. And the gradient is also the normal to the level curve passing through x0, provided that fx and fy are continuous at that very point. For a directional derivative, let omega be a subset of Rn, and let f be a function of the mapping omega into R. Let A be an interior point of omega and U be a unit vector in Rn. The directional derivative of f in the direction U at A is defined by the derivative of f with respect to U. If the limit exists. And the directional derivative of f in the direction U at A is given by the dot product of the gradient and the direction U. So let's do another final question. Let f, x, and y equal x squared minus 2y cubed. Find a unit vector in the xy plane which points in the direction of greatest increase of f at the point 1, 2, and find the directional derivative of f at the point 1, 2 in the direction of the vector I minus j. So the direction of the greatest increase should be parallel to the gradient of f. So let's compute this first. Yep, so if we remember, f is equal to x squared minus 2, or x squared I, sorry, minus 2y cubed j. X squared minus 2y cubed. And then so our gradient formula is given by df on dxi plus df on dyj in 2 dimensions. So we end up getting the gradient of f to be 2xi minus 6y squared j, and if we substitute the point 1, 2, we get 2i minus 24j. So hence the unit vector pointing in this direction is equal to 2i minus 24j over the magnitude of this gradient, which is equal to root 580. And when finding the directional derivative, we must find the unit vector of I minus j. So here we know that it's simply just 1 over root 2 times that same vector. So hence the directional derivative is given by the dot product of the gradient times the unit vector of the direction we want to pick, which is equal to 2i minus 24j, and its dot product with 1 over root 2i minus 1 over root 2j, and that should just be equal to root 2 minus, plus 12 root 2, which is, 13 root 2. That's your directional derivative at the point 1, 2. So for a surface S defined by phi is equal to a constant value, the tangent plane at P in S is the plane through P with the normal that's equal to the gradient of phi. From this definition, we can immediately write down the point normal form of the tangent plane at P, which is that the gradient and its dot product with a point x minus p should equal 0, where x equals x, y, z represents a point in the space, and p equals p1, p2, p3 should represent the coordinates of point P. For surfaces in R3, the normal line at P is the line normal to the tangent plane at P. So here, find the tangent plane and normal line to the ellipsoid 2x squared plus 2y squared plus z squared equals 8 at the point 1, 1, 2. Let f x, y, z equal 2x squared plus 2y squared plus z squared. Then we have our gradient to just be equal to 4xi plus 4yj plus 4zk with some simple differentiation. And then substituting the point 1, 1, 2 into the gradient, we have the normal vector n is equal to 4i plus 4j plus 4k. Always. Yep. Sorry, the gradient should actually be equal to 4xi plus 4yj plus 2zk. My bad. And then here, when we substitute the point 1, 1, 2, it's just (4i) plus 4j plus 4k. So now we can substitute this into the vector plane formula. X will be like x, y, z minus 1, 1, 2, and its dot product with 4, 4, 4 should equal 0. So 4x minus 1 plus 4y minus 1 plus 4z minus 2 equals 0. And as you can see, that gives 4x plus 4y plus 4z is equal to 16. So let f be a function mapping from R2 to R. A critical point of f is a point AB where the gradient is either 0 or does not exist. And then a stationary point of f is a point AB where the gradient is 0. So a function f has a local maximum or minimum at AB if f at AB is the largest or smallest function value on some small disk centered at that same point. So basically, if the gradient of f at a point A is equal to 0, then we consider it a stationary point, and it is a global maximum if fa is greater than or equal to fx for all x in the set omega, and it is a global minimum if fa is less than or equal to all of the values of fx. It's a local maximum if there is an open set around A such that fa is greater than or equal to fx, and a local minimum if there is an open set such that fa is less than or equal to fx. It is and the point A would be a saddle point if it is a stationary point, but it is neither a maximum nor a minimum. So for the second derivative test, suppose the second order partial derivatives of f are continuous on a disk with center AB, and that the derivative of f with respect to x at the point AB and the derivative of f with respect to y is equal to 0. This means that AB is a critical point. So let the discriminant be defined by the second double derivative of f with respect to x multiplied by the double derivative of f with respect to y minus fxy squared. So if d is greater than 0 and fxx is greater than 0, then the point is a local minimum. But if d is greater than 0 and fxx is less than 0, then fab is considered a local maximum. If d is less than 0, then we just consider it a saddle point. And if the discriminant is equal to 0, or d is greater than 0 but fxx is equal to 0, then the behavior is undefined. So let f be the function x cubed plus 3x squared plus 24xy plus 12y squared plus 15x minus 2. Show that 1 minus 1 is a saddle point for this function, and show that f has one other critical point, and find out what type it is. So first thing to do is to find all the derivatives of this function with respect to x, y, or the second derivatives. So if we differentiate everything with respect to x, we end up getting 3x squared plus 6x plus 24y plus 15. Differentiate everything with respect to y, we get 24x plus 24y. To get fxx, we differentiate fx with respect to x, so that's just 6x plus 6. To get fxy, we can either differentiate fy with respect to x or fx with respect to y, and you should end up getting 24. And similarly, for fyy, we end up getting 24 as well. So we first showed that 1, -1 is a saddle point for f. So we have the three values we want to determine what the value of the discriminant could be. So fxx fyy minus fxy squared is equal to the discriminant. In this case, 6 plus 6 times 24 minus 24 squared equals -12 times 24, which is clearly less than 0. And since d is less than 0, 1, -1 is a saddle point. And we also want to show that f has one other critical point and find out what type it is. So the gradient of f is given by the function over here, where this is fx and this is fy. Setting this value at 0 and solving it gives us critical points at 1, -1, as well as 5 and -5. So if we equate both of these derivatives to 0, we end up getting the relation (24x plus 24y equals 0, which means x equals -1, and also 3x squared plus 6x plus 24y plus 15 equals 0. So here, 3x squared plus 6x minus 24x plus 15 equals 0. So 3x squared minus 18x plus 15 equals 0. And when we solve for this, we end up getting x minus 5, x minus 1 equals 0. So hence, x equals 5 or 1, which means that y equals -5 or -1. So if we substitute 5, -5 into our discriminant, we end up getting, if we remember, that fyy is equal to 24 and fxy was equal to 24 as well, but fxx is equal to, I think it was 6x plus 6. Yeah. 6x plus 6. So when we solve for this, we end up getting 6 times 5 plus 6, which is equal to 36, times 24 minus 24 squared, which is equal to 36. 12 times 24, which is obviously greater than 0. Since we know that since a discriminant, fxx is equal to 36, which is greater than 0, then 5 is a local minimum. Sorry, negative 5 is a local minimum. And then Lagrange multipliers. Suppose that f are differentiable and s, where x is a subset of Rn, and this function is equal to c, defines a smooth surface in Rn. If f attains a local maximum or minimum at a point A, then the gradient of fa and gradient of the other function are parallel. And if the gradient of the other function is not equal to 0, then there exists a Lagrange multiplier such that we obtain this expression over here. So a rectangular box has 3 of its faces on the coordinate planes and 1 vertex in the first octant of the paraboloid. Z equals 4 minus x squared minus y squared. Determine the maximum value of the box. So first we define the volume of the box to be x, y, z, just because it's a rectangular box. And the constraint we are given can be rewritten with all these variables on one side. 4 minus x squared minus y squared minus z. And since these vertices are in the first octant, we know that all of these values must be greater than 0. So the gradients are given as follows. And now we should check that the gradient of gx is not equal to 0 for all x on the constraint. So clearly, based on this, gx on the gradient can't be equal to 0 because it has a constant term. And now the maximum on the paraboloid must satisfy fx is equal to lambda, gradient of fx is equal to lambda gradient of gx, and gx equals 0. So this gives us the following systems of equations. Yz equals negative 2 lambda x, xz equals negative 2 lambda y, xy equals negative lambda, and x squared plus y squared plus z should be equal to 4. So we can divide the first 2 equations by the third to get yz over xy equals negative 2 lambda x on negative lambda. So z on x equals 2x, which means x squared equals z on 2. And a similar expression can be obtained for y to get y squared equals z on 2. So finally, we substitute that back into our constraint equation, where we get z on 2 plus z on 2 plus z equals 4. So 2z equals 4, z equals 2, meaning that the point gives a max volume of 2. And that the point is 1, 1, 2. Okay, now for double and triple integrals. So let's go through Fubini's theorem first. Suppose that f r into r, let f be a continuous function on a regular domain between AB and CD, then basically if these conditions are satisfied such that f is continuous, then we can actually just kind of rearrange the order of integration. So let's practice over here. calculate the double integral of y sine xy over the domain R with respect to dA over the region R equals 1, 2 and 0 pi. So since y sine xy is continuous over R, we can apply Fubini's theorem to rearrange the integral from this to integrate dx first. And then integrating y sine xy with respect to x should just yield negative cos xy. If you just apply a quick u substitution, you'd end up getting that. And then we substitute y equals 2 and 1 into that to get negative cos 2x plus cos x. And then we integrate again to end up getting negative sine 2x on 2 plus sine x. Substituting our values, we actually end up getting 0. And now use double integration to find the area of the region bounded by y equals square root x, y equals x, and y equals x on 2. So something to note is that let's say we were to roughly draw out our graph. Let's make y equals root x black, y equals x red, and y equals half x like blue, something like that. So you can see we have two distinct regions cutting off at the intersection of y equals x and root x, which is clearly equal to 1. And since they all intersect at 0, we also want to have a look at when y equals half x and square root of x intersect. So basically x squared is equal to 2x. I'm sorry, 4x, and that means x is equal to 4. So we have our two regions that we can apply our double integral on. Basically, if we find a double integral of 1 with respect to an area, then that gives us the actual area of the region. And since y depends on x, we want to integrate our integral with respect to y first. Then we integrate it with respect to x. Doing it out of order may yield a different result. So integrating those two, we end up getting those two functions here. And then further integration will yield an answer of 7 on 6. Note that this can be simplified to x on 2, and this can be rewritten as x to the power of half minus x over 2. Okay, and then now we move on to double integrals using polar coordinates. So use polar coordinates to find the double integral of x squared y cubed with respect to dA, where omega consists of the region where x squared plus y squared is less than or equal to 1, and x and y are both greater than or equal to 0. So we note that for polar coordinates, x squared plus y squared is equal to r squared, sorry. So since r squared is less than or equal to 1 and presumably greater than or equal to 0, then it holds that r is less than or equal to 1 but greater than or equal to 0. And since both x and y are greater than 0, then we know that theta must be in the first quadrant, so between 0 and pi on 2. So these will become the bounds on our double integral. We let x equal r cos theta and y equal r sin theta, so that dA is equal to r dr d theta due to the Jacobian. And so we end up getting the integral over here. Where if we substitute x equals r cos theta, y equals r sin theta, and replace dA with r dr d theta, we end up getting r to the power of 6 times cos squared theta times sine cubed theta. So let's start integrating this. If we integrate with respect to r first, since this is basically a partial derivative or integration, we can assume that theta is constant in this case. So integrating r to the power 6 gives r to the power 7 over 7. And with the boundaries of 0 and 1, that's just equal to 1 on 7. And note that we also split up one of the sine squared thetas into 1 minus cos squared theta, since the power of cos is even but the power of sine is odd. And then integrating this expression with respect to theta, we get negative 1 on 3 cos cubed theta and 1 on 5 cos cubed theta. And if we were to do the math, we should get something equal to 2 over 105. And now find the formula of the volume of the tetrahedron bounded by the plane given by this equation over here. So we rewrite z in terms of x and y, and then rewrite y in terms of x, since the limits of y will be derived from the projection on the xy plane, where z is 0. So here, these are the limits upper limits we end up obtaining, and we're also given the lower bounds from the question. So finding the volume just involves the triple integral of 1. And we set up our integral as follows. So since it's 1, when we integrate with respect to z, we just end up getting the upper bound in our equation here. So something like this. And then integrating this, we get c y minus xy on a minus y squared on 2b, where we substitute the upper bound, since the lower bound is just 0, all of these values are just 0. And then expanding that out, we get this long expression, which can be simplified to b on 2 minus bx on a plus bx squared on 2a squared. And when we substitute a, we end up getting abc over 6. Okay, so now for cylindrical coordinates, instead of using if we want to map an x function f, x, y, z into cylindrical coordinates, we first convert each of these into their respective cylindrical coordinates. So z is just equal to z, r is equal to r cos theta, x is equal to r cos theta, and y is equal to r sin theta. As we see here, if you were to rotate theta by 2 pi, you'd end up getting a whole circle, and since you're rotating around r and z, you should end up getting a cylinder as well. Something like that. And here you can see that if we were to draw a right angled triangle with respect to the x-axis down here, that the x coordinate is equal to r cos theta, and the y side is equal to r sin theta. And note that when we're converting from Cartesian to cylindrical coordinates for integration, we should multiply by the Jacobian, which is equal to just r. So we'd switch the bounds we're integrating with respect to this. So let's practice this question. Evaluate the volume given by this function. So as stated earlier, we let our bounds, we convert the coordinates first to cylindrical, and the bounds for r and theta are kind of given here, where since x squared plus y squared is equal to 16, which is equal to r squared, then the bounds for r are between 0 and 4, and since we're rotating through the entire xy plane, or 2 pi around the z-axis, the bound for theta is also equal to 0, 2 pi. And then since x squared plus y squared is equal to r squared, we know that z is equal to r on 2, so that will be our upper bound for z. So rewriting the equation gives us this, where x squared plus y squared is equal to r squared. And then the r is just basically the Jacobian determinant that we have to multiply by when switching coordinates. So we end up getting this expression over here, which is just r to the power 5 on 2. And then now integrating with respect to r gives us r to the power 6 on 12, and we multiply that by 4. So as the last part of our integral, we end up getting 4096 times theta on 12, where theta is equal to 2 pi, and that can be rewritten as 2048 pi on 3, which gives us the value of our triple integral. And now spherical coordinates are slightly different, because now we're actually converting Cartesian coordinates to something that easily allows us to find the volume of a sphere. So in this case, we actually use rho, phi, and theta, where theta represents the azimuthal angle, which is just the angle mapped on the xy plane, and phi is the angle stemming from the z-axis. Rho is just the magnitude as usual. And note that here, x will be equal to rho sine phi cos theta, y equal to match this side over here, where instead of our magnitude being r, it's just rho sine theta, or not rho. And then y is equal to rho sine phi sine theta, and z equals rho cos phi, this axis up here. So express the volume V of the region above the cone, square root of x squared plus y squared, and inside the sphere, x squared plus y squared plus z squared equals 2az using spherical coordinates, and evaluate the volume. So let's draw it out first. On a 2D plane, let's say the xz plane, the area we're integrating through kinda should look like this area over here, and you just rotate that about the z-axis. So in essence, we're integrating with respect to phi over here, and we know that since it's all around the z-axis, our boundaries for theta would be in between 0 and 2 pi. And we'll just later find the boundaries for whatever rho is. So using the sphere equation, we end up getting rho squared is equal to 2ap rho cos phi, which means that rho extends from 0 all the way up to 2a cos phi. And then to find the limits for phi, because we know that theta's limits are between 0 and 2 pi, we should just find the vertex angle of the cone as mentioned earlier. And this can be done by equating the cone equation, which was z equals square root of x squared plus y squared. Expanding that out further should give us rho tan phi is equal to 1, which means that phi lies between 0 and pi on 4. And now we write out our integral as follows, noting that the Jacobian determinant in this case is rho squared sine phi. And so now we integrate this expression. I prefer to just do rho first because obviously it is dependent on phi. So we end up getting rho cubed sine phi over 3, which gives us 8a cubed cos phi cubed sine phi over 3. Then we integrate with respect to phi to get negative 8a cubed cos phi to the power 4 over 12, with the boundaries pi on 4 and 0. So here cos 0 to power 4 is equal to 1, cos pi on 4 to power 4 is equal to 1 on 4, which gives us the expression down here. And then when you evaluate it, that should end up being pi a cubed. So the volume of that region that we were given is just pi a cubed. And then for a change of variable, let omega be a subset of Rn and f be a mapping such that of omega onto Rn, be an injective and continuously differentiable function such that the determinant of the Jacobian fx is not equal to 0 for all x is in omega. If f is any function that is integrable on omega dash equals f omega, then we end up getting this expression for a change of variable. So as mentioned earlier, with polar substitution, we substitute our values and multiply by the Jacobian determinant, which is given by this. And that's just mapping the different functions. So evaluate the double integral of x plus 2y squared xy dx dy, where omega is the region in the first quadrant bounded by the curves y squared equals x, y squared equals x minus 1, xy equals 1, and xy equals 2. So first we plot out our region, which is given by this Desmos curve over here. So these lines correspond to y squared minus x. This one's y squared minus x greater than or equal to 0, less than or equal to 1. And these curves up here correspond to x, y is less than or equal to 2, x, y is greater than or equal to 1. So this is the region we're looking for. And now let's define u equals x minus y squared and v equals xy for the sake of simplicity, because those were our given boundaries there. So the Jacobian with respect to x and y is equal to this matrix over here. So if we were to work it out, remembering that u is equal to x minus y squared and v is equal to xy, we end up getting this matrix over here. And the determinant of f, Jacobian of f, is equal to the inverse of the determinant of Jacobian of g, the reciprocal. Yep, so we know that the determinant of g is equal to 1 times x minus negative 2y dot y equals x plus 2y squared, as given here. And from the boundaries we were given earlier, u is between 0 and 1, v is between 1 and 2. So the integral is now this expression over here, where this is the Jacobian determinant and you can see that since these two are essentially equal, we can just cancel them out to obtain this simple integral over here. Integrating that with respect to u, we just get v, and integrating this with respect to v, we get half v squared, and that's just equal to a half. I'll hand it over to Oscar now.
Alright, thank you very much. Okay, so moving on, we're going to start with vector fields. So vector fields is the next topic we're going to be looking at. Alright, so we'll get cracking with it. So, I guess starting vector fields, we might as well introduce what a vector field is. So, in simple terms, a vector field is just a function that takes vectors in and it outputs vectors. So, in 3D space, we can think of a vector field as 3 real valued functions, which is going to be f1, f2, f3, and these give us our corresponding, I suppose this here is a vector. And so is this little x thing here. So we're putting in a vector and we're getting out a vector. So nothing too crazy. So if you want to sketch a vector field in the 2D plane, hopefully 2D, sketching that in 3D would be a nightmare. All you really have to do is you just think of an individual point, you plug that in, and you draw the vector corresponding to that point by substituting it into your vector field. So, so at each point x, we draw the corresponding arrow given by this. So, this is an example of what a real-life vector field looks like. We actually can apply this stuff in the real world, which is great. We're not learning this for nothing. So, this is what a vector field might look like. This is a wind map. And you see that you pick any individual point here, and we have a corresponding vector that goes around like that. So, yeah, this is just kind of like a fun little fact. This is what one might look like. So, we're going to introduce, this really important vector differential operator, which we call the gradient, or has a fancy name, nabla, which is this upside down triangle. So we say that the gradient of a scalar function, which is just this, is the vector given by all of its partial derivatives. So what you do is you take the scalar function, take the partial derivative with respect to x. You get the x component of the vector field. Partial derivative with respect to y, you get the y component of the vector field. And you keep on repeating this for however many variables you have. In this course, we only really need to worry about, I guess, 2 variable functions and 3 variable functions. We're not going to have to compute gradients of massively functions in Rn. So yeah, all it is it just takes the partial derivatives of our function and it throws it into a vector. And we'll see why this stuff is very important later on. But there's more that we can do with nabla. So this gradient takes scalar functions and gives us vector valued functions. Now suppose we want to do something with nabla and a vector valued function instead of a scalar function. We can compute something called the divergence. So the divergence at some point P, you can interpret it as the total outward flux. So what this might look like is if we have some region. That's a bit dodgy. I'll draw a better one. So you have some region like this, and suppose we've got like a magnetic field or some kind of vector field moving around like this. Okay. Then if we computed the divergence of this region, it's really just telling us how much is our vector field passing through this region and how much of it is exiting the region. So it's just, I guess in other words, the flux that's going through it. So that's a nice kind of intuitive way to think about divergence. So how do we actually calculate divergence? Okay, so suppose that we take some vector field given by f1, f2, f3. So the divergence, you can just take the dot product with nabla. And it's quite nice. We can think of nabla as a vector. So I like to draw a little arrow above this. And we can think of it as the vector we can think of it like this, right? It's a vector. Well, you can think of it like a vector, right? It's a vector, and each term is like is a derivative operator. So then when we take the dot product, we just dot our derivative thing with the first value in our vector field, f1. So, oops. So you'll see that gives us this term here. And then we just repeat that. So all we're doing is we're just summing the partial derivatives, and it's no longer a vector valued function, it's a scalar value. So yeah, an example of this might be ocean currents. Say you've got some control volume underwater and you want to talk about, okay, well, how much water is passing through this point? You could calculate the divergence of that region and it'll give you that value of everything passing through, the net current leaving that point. So negative divergence indicates net inflow. So we might have a point like this. And if we have stuff going in like this, you might have heard this referred to as a sink. This is when the divergence is less than 0. And then if you have a positive divergence, it means that everything's sort of coming out of it like that. It's being pushed away. And this is when your divergence is positive. And we call that a source. So you don't really have to worry about sources and sinks, but that's just kind of a bit of terminology. Okay, so now we're going to actually use this nabla thing, and we're gonna try and prove this this little identity that they've got here. So suppose that R, our position vector, is just the general position vector in 3D space, just given by x, y, z, and we'll denote the magnitude of this vector, or the norm of this vector, by this. We want to show that nabla of 1 over R, or 1 over the magnitude of this vector, is equal to negative R divided by its magnitude cubed. Okay, so the first step we need to recognize here is that the norm of R is just given by that, right? We're summing the squared components and taking the square root. We're just using the Euclidean norm, right? This is just standard vector magnitude stuff. So 1 over R, non-bolded, so 1 over the magnitude is going to be this expression here, like that. And now we hit it with a nabla. We hit it with a nabla right here. So we've got to think, okay, so we're applying nabla to a scalar function. So we take x partial derivatives, that's the x term. We take the y partial derivative, that's the y term, etc. Right? So if we take the partial derivative of this, we're going to end up with, say we hit it with a d on dx of 1 on r. So we're going to bring the negative half to the front, and we're going to take the partial derivative of x from the inside. So that'll be times 2x, and then we leave everything else. So this is just like high school chain rule stuff. And then we subtract 1 off the power. So you'll notice that this and this will cancel. So then we get negative x over x squared plus y squared plus z squared to the half. And this whole thing's cubed because we've got that 3 there. So this is just negative x over r cubed. Okay, so that's our x partial derivative. I mean, you can sort of see that there's a symmetry in our norm here, that if we do the same with y and the same with z, we're going to get the same expression, but we're just going to substitute, instead of an x, it's going to be a y and a z. So we can just say that, okay, we're going to get this same term out the front every single time. So we'll just throw it out the front, and it's always negative, and then we're just left with x, y, z. So this thing here is precisely our vector r. And this thing here is precisely r cubed. So we arrive at the conclusion that we've got negative r over r cubed. So it's just a simple find the norm, apply the gradient to it. Very nice. Okay, so now there's even more that we can do with this nabla thing. It's very useful. There's so much we can do. And the next thing we're going to look at is curl. So curl is, intuitively, it's a measure of how much does a vector field swirl around a particular point, or how much does it curl around a point. Convenient naming there. So we can define the curl as the cross product of nabla with the vector field. So this is again thinking of nabla as a vector. It's like you can get away with thinking of it as a vector, as we did before. So you can calculate this two ways. You can either do a determinant. I don't really like to do that because it's a bit time consuming. Or you can just kind of draw the two vectors and cross match up the terms. So this is what the curl of a vector field is. So if the curl of a vector field is 0, we say it's irrotational, which intuitively curl is how much it rotates. If it doesn't have any curl, it doesn't rotate. So in a 2D vector field, right, this kind of begs the question, like, how do you take the cross product with a vector that only has 2 components? Well, that's a great question. We just say that the third component of the vector field is 0 and treat it like a 3D vector. So then we can calculate the curl. So we can calculate the curl of 2D vector fields just by letting the last component be 0. Sweet. Okay. And if we are doing this 2D thing, our curl is always going to be this z curl. And it's, so the third component of the curl is always denoted by this, and this is, the general expression. So this is important because we're going to see this come up when we look at integral theorems, particularly Green's theorem. So for 2D vector fields, the z curl of f at a point is the anti-clockwise rotation about that point. So if you're kind of looking down like on the xy plane, so this is x, this is y, this is z, we're kind of observing how much does our vector field swirl around in this like xy plane here. Okay, so if the curl is negative, we've got a clockwise rotation. So this is just sign convention. Okay, so here's a problem. We've got a vector field, very nice, v. Now we're going to calculate the curl of this thing. Okay, so there's 2 ways that you can do this. And the first way is the more intuitive, approach it head on, just like hit it with a cross product. So when we do the cross product, so we match this with this to get d on dy of xy, which equals x, and then we do this with this, and then we subtract d on dz of xz, which equals x. So then we get x minus x, like that. Okay, so then doing the cross product for the next term, we match up this with this, subtract this with this, which gives us y minus y. And then for our final term, we do this with this, subtract this with this, which gives us z minus z. So conveniently, our curl is 0. Okay, so this is the proper way of doing it. But if you're kind of sneaky, you can notice, or you can recognize that the vector field that we have here is actually a conservative vector field. And I say conservative vector field, meaning that it can be expressed as some scalar, nabla of a scalar function. And we have a property that the curl of any conservative vector field is always 0. Conservative vector fields always have 0 curl. You can prove that yourself using Clairaut's theorem or the mixed partial derivative theorem if you want. I'm not going to go over that now. But yeah, you can recognize that it's a conservative vector field of the form that. Therefore, the curl must immediately be 0, which saves you a bit of computation, but again, harder to spot. Okay, so that's kind of like everything that we need to know for vector fields. So we're going to kind of apply this to line integrals and surface integrals. This is the real application of this stuff. So a line integral, similar to a path integral, but similar to like a path integral over a curve, but we're integrating a vector field. So we're integrating a vector field over some curve, and it has this form here. And intuitively, you say that S, some curve S, you can describe it by some path C. So then when we have ds on dt, we just get c dash t, therefore ds is c dash t dt. Okay, so if we're going to convert our ds into our ds in the integral here from a vector valued thing to a scalar valued thing, which is a lot nicer, we multiply by c dash, and obviously we plug the parametrization into our vector field. Okay, so C needs to be continuously differentiable, and it's an oriented curve. So we've done a lot with oriented curves, we're kind of used to this stuff, and our parametrization has to be consistent with the direction of our orientation. So, yeah, what this notation here is saying is that it's interpreted as the integral of the vector field along the tangential component of the curve. So the ds here is just the tangential component of our curve. Okay, so we oftentimes write line integrals in this form, which is just by saying that s or ds is like a vector dx, dy, dz, and f is a vector field m, n, p. Dot product immediately gives us this expression. So oftentimes we see it in this form. These are of course the components of the vector field, and we're given some parametrization like that. Evaluating that dot product gives us the expression here. Now, but that's not really a great expression. We want to try and parametrize it and get it all in terms of one variable t, so then we can nicely integrate the whole thing. So we evaluate, by doing that same thing that we had up here, where we were taking the derivative c dash, the derivative of the path with respect to t. It allows us to plug that whole like parametrization thing in, and we get this, which is nice because now everything's in terms of dt, and we can integrate it. Fun fact, the work done by vector field along some curve C is just the line integral of the force. Okay, so let's try evaluating a line integral over the unit circle. Okay, so unit circle is important. I'm going to underline that. That's very important. So first, we want to parametrize our curve C. Now, we're told it's unit circle. Okay, very nice, fantastic. So we can just use the standard parametrization of a unit circle, cos t, sin t. And we want to trace out a full revolution around the unit circle, so t goes from 0 to 2 pi. So nothing too crazy. So we need to get our dx's and our dy's in terms of dt, right? So we have some like consistent differential that we can integrate the whole thing with respect to. So we compute the derivatives of our parametric curve. We're computing the derivatives of c. So dx on dt is the derivative of cos t with respect to t, so we get negative sin t. Same thing with dy dt. So we can then say, well, dx. Oh, whoops. Hold on. This is why being left-handed is bad. Okay, so we get dx is negative sin t dt, and vice versa for dy. Very nice. So we just take all this and we just throw it into an integral. Now everything's in terms of t. Happy days. Okay, so we have cos squared t minus sin squared t, cos squared t plus sin squared t. It's just 1. Whole thing cancels very nicely, and then we kind of just have a trivial integral. So it's just 2 pi. And that's how we calculate that line integral. Very nice. Okay, so we should go over some properties of line integrals, some nice things that we can do with them. They preserve linearity. So if you add 2 vector fields and you're dotting them, you can split them up into 2 separate integrals. And if you have a scalar times a vector field, you can just throw it out the front of the integral. So it's quite nice. Now if we reverse the orientation around the curve, the integral becomes negative. So this is very important. This will come up later. Then if we have C is the union of some like smooth curves, so if you want to partition your curve up into a bunch of smaller curves, then you can just evaluate the line integral on each part separately and add the whole thing together. So that's, again, that's a bit more work. It's nicer if we can just do the whole, smash it out all in one hit, but it's just a thing that we can do. Okay, so now we're going to try a question. We're going to keep this stuff in mind, particularly reversing the orientation. This is very important. So consider the vector field 1, 1. Okay, so this is a constant vector field. This vector field does not change. It is, I guess, anything that has the same gradient as the line y equals x. So it's going, we've got a vector field that's a bit like everything kind of going up in this direction. And I'm just going to get rid of this for a sec because I want to draw a curve. So, and we have a curve C which joins the points 1, 0 to 0, -1. Okay, so it joins it down here. And then it joins it to -1, 0. And then it joins it to 1, 0, like that. Okay, and then now we're going to draw the vector field in. We're going to draw this in because this is now, it's going to be like that. And note that this is actually perpendicular here. Okay, so is the line integral of this vector field over our curve negative or 0? Positive, negative, or 0? And why? Okay, so we're going to use the fact that we can split up line integrals as the sum of, we can partition the curve up and just compute each line integral separately. So we first start by considering this perpendicular side here. Since the line integral is the measure of the tangential component of the vector field against the curve, this is perpendicular. There is no tangential component. So for this, part at right angles here, we simply have that the line integrals is 0. It's just 0 because the whole thing's perpendicular. There's no work being done. Now, if we consider the side here, if we consider the side here, like C1, then, okay, say that there is the integral like that, and then if we consider this like C3, which is the integral on the other side, notice that the two curves C1 and C3 are the same, but the orientation is just reversed. So because the orientation is reversed, that means that this here is equal to, I guess I'll write it on the other side. It means that this integral here is negative. It's the negative of the integral on the other side. So because the orientations are reversed and the vector field is constant, they just cancel out. So in total, our whole line integral just goes to 0. So here's it worded if you want to read that. But yeah, it's just the same thing that we've been saying. The two parallel sides cancel each other out, and then the perpendicular side is just 0 because there's no tangential component. Sweet. Okay, so now we're going to jump into some integral theorems. So if f is a conservative field, which means that it's the gradient of some scalar field, I've jumped the gun. Yeah, we say it's conservative, or we call it a gradient field. And we also say that phi, our scalar, is the potential function for f. Okay, is this loading? Okay, we'll just give this a second to load. Doesn't seem to want to load. This is weird. Oh, okay, yeah. Okay, so for some reason the slides that have this stuff not like grayed out doesn't want to load, so we're just going to try and read it here. So we've got something called the fundamental theorem of calculus for line integrals. Which is very similar to the fundamental theorem of calculus you learn in high school, except now it's line integrals. So if we have f being some conservative vector field, written as f equals nabla phi, then over some curve C, and I'll draw a diagram of what this looks like. So this is C, and this is the point A, B. Then if it's a conservative field, we don't even have to really evaluate the line integral. We just evaluate the potential function at these endpoints. So this is kind of analogous to it's actually the exact same thing. So, but it's just kind of like a vector calculus analogy. So if we have a conservative field and we can find what the scalar potential function is, we don't have to compute the integral. We can just substitute the endpoints in and subtract them. That's all this theorem is saying. Oh, now it wants to load. Okay, so yeah, so we've kind of covered all this. Okay, now I really like this theorem, so I've thrown a proof in here. You can look at this in your own time if you want. I'm not going to spend too much time going over this because it's a bit meaty. But yeah, we just use the chain rule and fundamental theorem of calculus. So that's how we get that result. So if you're interested, you can pause the video and give this a read, but we're going to move on. Okay, so here is an actual question. So we're going to evaluate this line integral given some vector field. And we're told that our curve that we're evaluating this over is a straight line segment from A to B. Okay, so that's the first part, evaluate the line integral. And then the second part is we want to show that the value of this integral is the same regardless of the path taken between A and B. So, spoiler alert, that means that only the endpoints matter. So therefore, f will have to be conservative. So we're going to try and show that. So we're going to tackle the first part. And we have to parameterize the curve. That's the first step always. We always parameterize the curve. So it's a straight line segment from A to B. So we can say that L is just this. So this is just kind of like vector line equations, extension 2 kind of stuff. So we get this parameterization for the straight line segment. Sweet. And we say that t at 0 gives us A and t at 1 gives us B. Okay, so we've got that path. Sweet. So t is from 0 to 1. Those will be the bounds on our integral a little bit later. So we find c dash t, we find the derivative because we're going to have to substitute that in. And now it's just a matter of plugging into our vector field. So we have that f equals yx2z. yx2z. And this is going to become our x, this is going to become our y, and this is going to become our z when we parameterize it. Okay, so we plug this in to the integral. So, yeah, so f of x, y, z gives us yx2z. So substituting that in gives us this. So this is our vector field. And this here is c dash t. So we evaluate this dot product, and we're just going to get 2t plus 2t plus 18t, which gives us our 22t that we've got there. Now, this is just a single variable integral. Sweet. Okay, so we just integrate that. We get 11t squared between 0 and 1. Sub in the values, we get our answer is 11. So that's the value of the line integral. So we've evaluated the line integral. Now we need to show that it's not path dependent. That it doesn't matter what path we take. So to show that this is the value is regardless. Sorry, the value is the same regardless of the path we take. We need to show that f is conservative. Okay. So we're going to begin by defining f as some conservative vector field nabla phi. And that means that if we take the x partial derivative of phi, it gives us the x component of our vector field. If we take the y partial derivative of phi, we get the y component, etc., etc. So now we're going to play a game of kind of matching up these variables all with each other. So we're going to get unknown functions in there, and we're going to try and rope everything in to work out what pieces are missing. So we'll start with this function. We'll start with d phi on dx equals y. So integrating, or it's not even really integrating, it's like reverse partial differentiating with respect to x. We get that the y becomes an xy, but then we also tack on this missing function f of yz, because note that when we take partial derivative, any function purely in terms of y and z will just disappear. So instead of a missing constant, we now have a missing function. So what we're going to do is we're going to take this phi here, and we're going to take the partial derivative with respect to y. So, yeah, now let's do that. And we have that this is equal to that by definition. So if we differentiate the function that we had up here with respect to y, we get the y disappears and we get left with an x, okay? And then we have the partial derivative of f over a partial derivative of f with respect to y. But we know that by definition, d phi on dy is equal to x, which we're told is x plus, which means that this has to be 0. Otherwise, these two sides wouldn't be equal. Okay, so we know that if we take the partial derivative of f with respect to y, we get 0. So that means that f is purely a function in terms of z. Okay, so we're going to redefine f of yz as g of z. Okay, so now going back to that original expression that we'd gotten, which was this one here, instead of writing f of yz, we write g of z. Now we take the partial derivative with respect to z, which was given right at the start by this. Okay, so the xy completely disappears and we just get g dash z. And this is just g dash, like it's a regular derivative because g is purely in terms of z. So we get that this here, using the thing above, is 2z. Now we just integrate with respect to z, we get z squared plus some constant c. Doesn't matter what the c is a constant, it's fine. Like, regardless of whatever that c is, we still have a scalar potential function for every value c. So we've arrived at this conclusion. We've got this expression for any arbitrary constant c, which implies that f must be conservative because we found a suitable scalar potential function. So that means, by the fundamental theorem of line integrals, it's path independent. Doesn't matter what path we take, it's just the endpoints that matter because f is conservative. Okay, so that's how we show that. Okay, so now we're moving on to my favorite theorem, Green's theorem. Love this one. This one's great. So this is great for finding line integrals on vector fields when we have like really horrific components, because we can just take partial derivatives and it oftentimes just simplifies something really nice. So suppose that D is a bounded simple region in R2 and it's got a boundary C which is oriented counterclockwise, the positive direction. So this might look like some region like this, and its boundary is going to be C, which is this counterclockwise oriented thing. Now, we have that these component functions P and Q are continuously differentiable on our region D. So if these things hold, if these conditions hold, we have this expression. The closed line integral of P dx plus Q dy equals this double integral across the entire region using partial derivatives. So I've thrown in a little proof of Green's theorem. This stuff is purely out of your own interest if you're interested. It uses some pretty complicated stuff, so you can pause this and have a look at this. I think it's very interesting. But yeah, you don't need to know this stuff, but you can pause it and have a look if you're interested. But yeah, so we're actually going to use Green's theorem now. So we're going to see why this theorem is so great. So we've got a line integral. It looks pretty nasty. Those component functions are quite rough. I don't even want to think about trying to like parameterize that and plug that in. So we're going to use Green's theorem. So we have our curve is the unit circle, positively oriented. Okay, so we have an xy simple region, bounded, and it has a positively oriented boundary, and these functions in here are elementary, so they're continuously differentiable. Okay, sweet. Green's theorem holds. So we let P equal this and Q equal this to get this in the form of Green's theorem. So we then evaluate our partial derivatives. So dq on dx gives us 3x squared, and then the partial derivative of P with respect to y gives us negative 3y squared. So when we subtract the two, we get 3x squared minus 3y squared. So we get 3 outside of x squared plus y squared. Okay, this is looking really good, considering that we're integrating over a unit circle. So yeah, by Green's theorem, we have this expression here. Okay, so you can see the left-hand side's horrific, the right-hand side's fantastic. Okay, so this is kind of screaming at us to do a polar coordinate substitution. So since C is a unit circle, intuitively we just perform the polar coordinate substitution. Let x equal r cos theta, y equal r sin theta, where x squared plus y squared equals r squared. So to perform a change of variables, we have to compute the Jacobian determinant, which is just this, which gives us r. So we know dx dy is just r dr d theta. It comes from the Jacobian. And our bounds are, since it's a unit circle, r is between 0 and 1, and we're doing a full revolution around the unit circle. So theta is between 0 and 2 pi. So the double integral becomes, okay, so this x squared plus y squared becomes an r squared. This becomes an r dr d theta. So we just get the 3 stays out the front there, and we just have r squared times r times dr d theta. So we get r cubed dr d theta, which is very nice. And notice that we have a rectangular region in r, like the r theta plane, so we can apply Fubini's theorem to just immediately pull this theta thing out. We can just throw a 2 pi out the front. Sweet. So we throw the 2 pi out the front from here and multiply it by 3 to get 6 pi. And now we just integrate the r cubed, so it becomes r to the 4 over 4 between 0 and 1. So our integral comes out to be 3 pi on 2. Very nice. Okay, so now we're going to get into some trickier integration stuff. We're going to look at surfaces in R3. So we have to introduce the notion of a surface parametrization. So suppose that we have some surface in R3. We call phi, the map from R2 to R3, a surface parametrization of S. So we can see that we've got some domain D, which is a subset of R2, and we're mapping everything from that to this surface here, which is a subset of R3. So intuitively, we have this mapping. Okay, so this is just kind of what it looks like. Now, we have to introduce a bit of terminology, a bit of cool stuff with surfaces. So for some surface S, parametrized by this, this map here, we have tangent vectors to the surface, which is given by the partial derivatives of our map with respect to the variables, the two variables that you parametrize it with. So in particular, the tangent vector in the u direction is just the partial derivative of phi with respect to u, and then the v direction partial derivative with respect to v. And just by a bit of geometry, we know that these two tangent vectors, if you take the cross product, you get something perpendicular to the surface. So that is what we define the normal vector as. Okay. So this is visually what this looks like. Okay, so how do we compute surface integrals? How can we throw all of this in to work out how to do surface integrals? So computing a surface integral requires parametrizing the surface. That's the first step. We need to find a suitable phi that maps out S on some domain. And then, once we've found this phi, if it maps out a smooth surface, you don't have to worry so much about what it means for a surface to be smooth. If you're curious, that just means that all of the component functions in your parametrization are infinitely differentiable. So they're all C infinity functions, if you want the fancy terminology. So so the surface integral given by this across a surface, we plug in the parametrization into F, and we multiply it by the normal vector. So this here is the normal vector. Where, again, this is how we define our tangent vectors. And then, yeah, we often write n as the cross product between these two, because it's just a lot easier than having to write out more terms. So we can compute areas of surfaces using this stuff, and I'll show you why this works. If we draw a surface in R3, something like this, with tangent vectors like that, say this is TU, TV, and then we've got like a normal vector here. When you compute the cross product of two vectors, say this is TV and TU, the cross product actually gives you, geometrically, the magnitude of this gives you the area. So this here is given by, so if we take these tangent vectors on the surface, compute the magnitude of their cross product, it'll give us a small area, it'll give us the area of a small surface patch, right? So obviously we apply the differentials here and we get this like infinitesimal area. So by integrating this whole thing over the surface, we're adding up all these like infinitesimal like cross product areas. So we get the area across the entire surface, which is really cool. So yeah, so to find the area, you just magnitude of the normal vector. Very nice. So yeah, so if it's smooth, we can parametrize it by, these are our kind of conditions for parametrizing. We don't have to worry too much about this. So let's actually try computing a surface integral. So consider the surface given by z equals x squared plus y squared. So we've got like a cool little paraboloid thing going on. And we have this kind of constraint here. Now we want to find the area of the surface S. So we can parametrize this very nicely because we have z in terms of x and y. So we can kind of eliminate z as a parameter to get it purely in terms of x and y, which gives us a suitable parametrization. So we've got x squared plus y squared. Okay, again, surface is smooth, everything in here is differentiable, very nice. And then we have xy is in some region D. And D is going to come from this, right? So this gives us like a unit disk in R2. So that's where we get this region from. Okay, so now we need to compute the normal vector. So we take partial derivatives of this with respect to x and y. So with respect to x, we'd get 1, 0, 2x, and with respect to y, we'd get 0, 1, 2y, which is this and this. Now, taking the cross product by just cross multiplying this, we get negative 2x, we get 0 minus 2y, and then we get 1 minus 0. It's a bit of a mess there, but we're just computing the cross product. And we get this is our resulting vector. This is the normal vector to the surface. So now we want to take the magnitude of this vector, right? We just take the standard Euclidean norm, and it gives us this thing here. Okay, so this doesn't look too great. So this is what our integral becomes by substituting that in, just by using that formula we saw before. Now, unfortunately, we have to apply a polar coordinate substitution to this because we've got this x squared plus y squared, and we also have that our region D is a unit circle, so naturally it lends itself to a polar coordinate substitution. So to compute this, yep, we just apply Jacobian, and we have these bounds. So the determinant of the Jacobian is r, so we have that r dr d theta, so that dx dy becomes r dr d theta, and we plug these in, we plug our values in, and now it's just a matter of simplifying this in here. So the cos squared theta and the sine squared theta just become a 4r squared, which we'll see in the next slide. It just becomes a 4r squared there, plus 1. So this is, quite a tricky integral. You can, you can just do a reverse chain rule here. You can just reverse chain rule this one. And the answer's not very nice, but that is the surface area via integration. So yeah, that's how you do that. A bit of work, but nothing too crazy. So now we can extend the notion of surface integrals to surface integrals of vector fields over surfaces. So yeah, it's not just something we do with scalar fields. So again, if phi is parametrization of an oriented smooth surface with some 2D domain D, then our our vector field surface integral is given by this. So not much really changes. All we're doing is we still have our normal vector in here. Okay, and then we still plug the parametrization into the function. The only difference now is we're just evaluating the dot product. That's the only difference. So, yeah. And you can sort of think this intuitively, like dotting the vector field f with the normal vector gives the component of the vector field that's tangent to the normal vector. So it's giving everything that's coming out of the surface from the vector field. So all the components of the vector field that are perpendicular to the surface. Okay, so now the big thing that we do with this is Stokes' theorem. So Stokes' theorem is pretty cool. So if S is a smooth oriented surface, okay, it's the same thing we've been seeing the whole time, and its boundary, ds, is oriented in the anti-clockwise direction when looking down on S from the positive direction, and we also have that f is continuously differentiable on S, then we've got this expression here. This here is Stokes' theorem, or I guess Stokes' theorem in R3, because there's a million different Stokes theorems. But yeah, this is the theorem that allows us to relate the surface integral to a line integral, because line integrals are much nicer to compute, surface integrals not so much. So it allows us to jump between the two. So I'll provide you a visual intuition for why Stokes' theorem works. So say I divide this region up like this, and we have the curl across the entire thing goes a bit like this. So this is the curl across the entire surface. So integrating this would give us the curl of f over our region. But notice that, I mean, if this were a physical kind of physical vector field swirling around, these components cancel each other out. They're in opposite directions, as do these, and these. They all cancel each other out because they're in opposite directions. So if we get rid of those, because they're cancelling, miraculously we just get the closed integral, or the closed line integral around the boundary. Sweet. So this is kind of a visual intuition for why Stokes' theorem works. So yeah, visually we can see this relationship. Okay, so now let's actually use Stokes' theorem. So I know I said that it's good that we can go from surface integrals to line integrals, and not so much the other way, but we're going to go the other way, and we're going to turn this into a surface integral. So let S be this surface defined by this, x squared plus y squared plus z. Sorry, x plus y plus z equals 0, so we've got a plane, and these are our bounds. And we have it oriented so that the z component of the unit normal is positive, and we've got this vector field here. So we want to use Stokes' theorem to determine this line integral. Okay, so our vector field's pretty bad. It's not very nice. Hitting it with the derivative would be nice though, so that's why we're using Stokes' theorem. So by Stokes' theorem, we can turn this into, I should probably put brackets around this. We can turn this into a surface integral of the curl. So we're going to evaluate the curl. So we just kind of cross multiply these terms to get our curl. I won't really go over that. We've computed a million cross products by now. So this here is our curl. Now we want a surface parametrization. So we had that x plus y plus z equals 0. So we can say that z equals negative x plus y. Keep the negative out the front. So that gives us our surface parametrization right here. Very nice. And this is a smooth surface. All our component functions are differentiable. Very nice. And we've now restricted it to two variables defined over this domain. Then we calculate the normal vector. Okay, so we take the partial derivatives of our surface parametrization and compute the cross product. So we get this, and it's very nice. We get a vector that's just all ones. Very nice. So we need to express n as a unit vector. So when we do these surface integrals with vector fields, n needs to be a unit vector. So we need to take the unit normal. Okay, so we plug in our curl. We get that. Dot Now this here is the unit normal. This is our unit normal vector, because the magnitude of that equals 1 on root 3. Now this is supposed to be dx dy. Okay, so we get this. And this is our region. We get a nice region here. So we just plug this in. This is a nice integral. So we can just plug the 0 and 1 on the x and y just straight into the integral and just start integrating. So this is now just a standard double integral, no fancy substitutions required. And yeah, so this, I don't really need to go too much through the working of this. This is just standard integration, plugging things in and simplifying. Okay, so we arrive at, that is the value of our line integral, so that there is that's what that's equal to. And we've just used Stokes' theorem to kind of simplify this to a really nice integral. Okay, so now we kind of push forward to our next theorem, our next integral theorem. Actually, the last one we're going to be looking at is the divergence theorem. So Gauss's divergence theorem allows you to compute surface integrals over closed surfaces. And it allows it, and we do this by throwing a triple integral in of a 3D solid bounded surface, or 3D solid that's bounded by some surface. So obviously some conditions need to apply. We have that our volume is bounded, it's solid, and it's a simple region. Okay, so we don't need to get too worked up with these definitions, but obviously just for the sake of a bit of rigor, we're going to throw these in. It has a piecewise smooth boundary oriented to the normal vector points outwards. So that means that it's bounded by some surface. There's some surface enclosing W. And if F is a C1 vector field on W, so that means that all the partial derivatives, all the first order partial derivatives of F exist on W. And the reason that that's the case is because we throw nabla in there. We compute the divergence. Now, if F was not C1 and the partial derivatives don't exist, then nabla.F doesn't really mean anything because those partial derivatives aren't really defined. So, yeah, we have this, we kind of arrive at this integral. So this is really helpful because it trivializes a lot of really complicated looking integrals. And we'll see, this is a great example of how we can trivialize these crazy surface integrals. So let W be the unit disk in R3. So when we say unit disk, that's just the unit sphere plus the entire interior, or the unit ball plus its boundary. Then let S be its surface, oriented to the normal vector points outwards. And then we have this vector field defined by this. So this one's quite a monstrosity. Now, if you wanted to try and compute the surface integral of this without using divergence theorem, be my guest. But I'm not going to be doing that right now because that is a lot of work. So we'll just apply the divergence theorem and we'll see how easily this simplifies. It's kind of crazy. So, of course, we need to check conditions hold. So indeed, W is bounded, solid, and simple. It's a closed unit disk in R3. S is piecewise smooth and oriented to the normal vector points outwards. And we have that F is C1 on W. In fact, it's actually C1 on all of R3. So I imagine they're not going to be grilling you on saying, show that the conditions of the divergence theorem hold. Show that F is C1 on W. They're not going to ask you necessarily stuff like that. They're more worried about, can you compute this integral? So this does hold, so we apply the divergence theorem. Okay, so we take the partial derivative of the x component with respect to x, the partial derivative of the y component with respect to y, and the z component with respect to z. So this is just the standard divergence of F. And you'll notice that all these horrifically complicated terms disappear completely. This goes, this also goes, and this goes as well. Okay, so we're left with 2, 1, and 1. 2 plus 1 plus 1 is 4. Nice. So what we've just said is that the integral of this really complicated thing is just that. Wow, like that's, it just trivializes the whole thing. And what's nice about this is this here is the volume of W. This integral here. Okay, so W, we said, was a region W, we'll go back here, is the unit sphere plus its entire interior. So it's literally just the volume of a sphere. And we multiply by the 4 out the front of the integral, and we arrive at this. So, yeah, again, note that this is just the volume of W. So we can see that we can take these crazy, like, horrific, closed surface integrals and trivialize it into something really nice like this. So these theorems are very powerful. They allow us to compute things that would otherwise be too difficult to compute. And that just about wraps up vector calculus and all of our integral theorems. So that brings today's seminar to a close. So we'll be running part 2 of this seminar tomorrow, same time, 11 a.m. to 1 p.m. And we're going to be smashing out all of complex analysis. So feel free to tune into that tomorrow. But yeah, good luck with your studies. Good luck with your upcoming exams. Hope this seminar was helpful. And yeah, have a great day.